Hi, we're going to start the afternoon session now, so keep to schedule. We've got 4 talks in the next session before the break. The first of those I'm just going to introduce now, Katalin, who is going to speak about insights from Glasgow Scottish Ambulance Service.
Which is Scottish Ambulance.
Yeah, and I'll leave the rest of the title to her because it's pretty long. Okay, and here's Catherine.
Yeah. Okay, so hello everyone. I'm Katalin, and I recently graduated. I will graduate in 2 days from University of Edinburgh with a master's degree in data science for health and social care. So I would like to talk about my final year project with the Scottish Ambulance Service, analyzing chest pain patient data from 2023. Okay. So a bit about the background of my project. So this chest pain patient data, it was the first time when this chest pain patient data was analyzed at all. Basically, it just provided, this project provided an overview of their data and the service evaluation, which was based on 6 clinical research questions relating to the emergency cause, the patient's past medical history, vital signs, symptoms, and treatment at the scene, and also the number of patients with suspected heart attack and those patients who were transported to hospital. So why chest pain? On the right, you can see in the table that chest pain can have many causes, from acid reflux to heart attack. And based on previous research, only 20% of patients who are calling with chest pain are diagnosed with cardiac conditions, and more than 50% of them are discharged without any serious findings. However, because chest pain can indicate a life-threatening condition, the call handlers tend to give higher priority to these patients. About the data, I received 14 data sets from the Scottish Ambulance Service, and most of these data sets contain data for over 50,000 patients. You can see it in green, like the call details, patient demographics, the patient's monitoring management at the scene, past medical history. But there were data sets which contained less data than this. For example, the pre-hospital medication data set contained data only for half of the patients who were calling. And there was a separate data set. There was a separate data set for the management of the suspected heart attack patients, which contained data only 16% of the calls. According to my clinical supervisor, that this number probably is higher because in the most urgent cases, the ambulance clinicians didn't record the data for these patients. I also received data sets related to with free text notes, free text data, for example, with the ambulance crew notes or the discussion details with discussion with the call handler. So, about the data cleaning challenges. First, with the help of my clinical supervisor, I had to understand what's behind the variables because there were a lot of terms or abbreviations I was not familiar with. There was also inconsistency in the CSV data files, which was probably due to system issues, like there were split columns when one column split into 2 containing different data. There were same variables in different data sets with different values. Also, there were mixed up column names where the data inside the column didn't match the variable name. And there were variables which should have been binary variables, but contained more than 2 values. Because of the time limit, I didn't have time for text mining for the free text variables, because some of them had more than 100 options, different options with no pattern, and sometimes they contained different data types, which I couldn't modify within the time frame. There were few which I could do. For example, the pre-hospital medication data set, because there were less options and I could see a common pattern. So I did the analysis mainly in R. I used 11 CSV files from the original files, and I selected 60 variables. So the most challenging part of this analysis was the cleaning of the data set, because, which included changing the data types, renaming variables, or creating new ones, like age categories or season based on the time of the call. During the result was presented mostly in tables and plots because it was a descriptive analysis. But I also did some basic statistical analysis to show differences between the different group of patients. You can see the R packages I used during the analysis. So some of the results I created in R. So this first one is a heat map which shows the distribution of the calls by geographic regions. You can see that most of the calls came from the Glasgow area, which is the most populated area. And the second plot shows how the distribution of call changed after I adjusted the numbers per 10,000 population. I used files from the internet containing the postcode and the coordinates for the UK, and I merged it with my data set based on the postcode. So that's how I created these heat maps. So the second one shows population pyramid, which shows the distribution of the calls by age and gender. You can see most of the call, there was a slightly more men called than women, but most of the patients were over the age of 70. And one thing was that more women called over the age of 70. Okay. So this stacked plot chart shows the distribution of calls by deprivation zone. The color represents the age groups, from the light purple one, which shows those aged below 30, and the dark blue shows the callers who were aged over 70. It shows that there were more younger patients calling from the most deprived area. Almost half of them were under the age of 60. In contrast, in the least deprived areas, most patients who called were over the age of 70. So, in conclusion, I hope that this analysis provided an insight how the Scottish Ambulance Service manages patients and record their data, and hopefully this can be used for future research, for example, linking the ambulance data with hospital outcomes, so we can see the whole journey of the patients from the call until the hospital outcome. And also, this data could be used in the future for developing prediction models to identify high-risk patients in order to reduce the healthcare cost of these patients. Thank you.
Thank you. We've had a couple of questions on Slack for you. One of those is, could you tell us about why R was the right tool for the analysis?
So it was in the description of this project when I chose from the university. So they advised me to use R for this project.
Thank you. And another question is, do you have a source for the 20% of chest pain are diagnosed with cardiac conditions?
Source?
A source. So where did that fact come from?
It was because I received separate data sets for everything, for the symptoms, for the treatments, and the details of the cause. And there was a small data set containing only 16% of the cause, which showed the patients with suspected heart attack. So it was from the Scottish Ambulance Service.
Thank you. Right, I think that's all the questions that have come through that I can see.
Mm-hmm.
Let me just double check, because I'm sure I saw another one. But I can only see 2 on here. So okay, it says there's 3, but then I can only see 2, so I'm not sure what that's about. But anyway, perhaps you could check the Slack channel afterwards and respond to it if there are any other questions. That'd be great. Thank you very much.
Thank you.
Thank you. So I think the next talk is Sebastian. Is Sebastian around? Oh, great. Thank you.
There you go.
Yeah, the microphone's just there. So this is Sebastian Fox, and he's going to talk to us about predictive modelling for health and social care capacity planning using open data. Thank you.
Great, thanks for having me. So I'm Seb Fox. I work in the Southwest Decision Support Network, and I'm going to talk to you about a project we've recently published. So I've got 2 objectives with this talk. I want to share a tool that we've developed that we've made publicly available, uses public data, which aims to help planners with planning rounds. But also, if I get time at the end, I'm aiming to share some of the learnings for areas that were new to me to help other people in similar situations. So, to explain the tool, the project brief was kind of visualized there. So, on the right-hand side of the screen, you've got some performance metrics at the top. These are the outputs. These are NHS performance metrics, so things like A&E 4-hour wait times or 62 weights for cancer, for the cancer weights. And then at the bottom, you've got the inputs, which are split into capacity and demand metrics. So capacity would be things like beds and staff and workforce. And demand are more kind of population-related things. So people in old age or risk factors and prevalence of disease, that kind of thing. So the aim is to, at ICS geography level, can we produce models that the inputs are demand and capacity levers, so things that we have control over, or we think we have control over, and can we predict performance? How accurately can we do this? Once those models have been built, can we then provide a tool for planners to access, to interact with the models that we've developed to plan for future scenarios? So the project breakdown that I'm going to talk about can be split into 4 sections. So reproducibility, data, methods, and implementation. So I've been working with R for 10 years now, mostly developing packages and data wrangling and visualization. So the first 2, I was very much in my comfort zone. The second 2, I was a little bit more out of my comfort zone, so that's where I'll talk about the learnings more. Touching on reproducibility, so I've mentioned I've done this in R, open source programming software. I did I obtained all the data, I cleaned it, I modeled it, and then I implemented the final tool using R. All the code's on GitHub in a public repo, so anyone can access it. It's all heavily documented, so hopefully people accessing it, including future me, will come to it and understand what I've done. I followed a kind of standard project structure and standard naming conventions, so easy to navigate through the project. And I've tried to control all the analytical and package environment using the RM package. for people this is new to, all this does take time, and it can take quite a bit of time, but I think it's really important for kind of longevity of projects to make them last. Onto data. So I've mentioned it all uses public data. There are challenges around this. So public data is published by different people. They publish at different frequencies. You have it, some is daily, monthly, weekly, quarterly, annual calendar, financial. So you have to bring it back to one standard unit of time. Some metrics have different start and end dates. Some change definitions over time, so you've got to be aware of that. Some of the geographies that the data are published at are also different. In a kind of the most challenging example of that was some of the metrics were published at ICB level, but they were just generally, like for the acute metrics, they'd be an aggregate of the acutes within that ICB. But the model I was trying to develop was trying to represent the ICB residents rather than the actual geography. So some residents in an ICB would actually be going to an acute trust in a different ICB, so had to account for that. And finally, COVID was in the data set, so I needed to somehow account for that. So the first step was to try and get everything into a tidy format. I've produced a big table with these columns, so year, org code, metric, numerator, denominator, and value. I mentioned obtaining the data programmatically. These were the packages I used, and a lot of data tidying. In the NHS and in government, we're quite keen on publishing Excel spreadsheets with merged cells and blank columns and blank rows. So I had a curious enjoyment of tidying that into a nice tidy data set. I realise there's someone talking about Excel a bit later, so I try not to be too mean. And then finally, the geography challenges that I faced, I overcame with the postcodes IOR package and Geosphere to understand distances between organisations. And a big shout out to the Organisation Data Service API, which helped me locate unknown organisations. So the final data set had about 20,000 data points for 55 metrics spanning up to 12 years. So it's not a big data set. It was quite a wide data set compared with its length, but the metrics in there were age, deprivation, risk factors like smoking and obesity, and lots of condition prevalence estimates from QOF. They were the demand metrics and capacity metrics around bed availability, bed numbers, staff absence and availability, and workforce FTEs in different staff categories and settings. And then also expenditure on mental health. There's a lack of information on the community and social care side, but I think that's, and I'd like to get more in there, but I couldn't find data sets on that. And then the current metrics being modelled are cancer wait times over 62 days, A&E wait times over 4 hours, primary care appointments over 4 weeks, and incomplete referral to treatment pathways greater than 18 weeks. So on to modelling. So we took a data-driven approach. We've done 3 kind of what I'm calling sophisticated approaches and compared them with 2 naive approaches. So the sophisticated approaches were using a logistic regression with an elastic net regularization technique. The output there was modelling a proportion outcome, so the proportion of A&E attendances over 4 hours. We also tried a random forest approach to do the same, and then we also used a random forest approach to model the change in proportion for the outcome variable from 1 year to the next. The naive approaches that we compared these results with were saying next year's value for performance is the same as this year, or drawing a straight line through the last 3 years and extrapolating it for a year. The data-driven aspect of this is we changed the data that we were putting in there. So we changed the number of years, we tried lagging some of the predictor variables, and we also tried lagging the outcome variable and using it as a predictor. We did hyperparameter tuning with using leave group out cross-validation, where we identified the groups as using NHS region, because we didn't want to overfit models where kind of validation set may have had the same ICB in it as the training set. So we split the training data into 7 folds and did that, and then we held out a test set to calculate the final evaluation metric on that. So this is a chart that I don't think anyone will be able to see, but it's got 4 charts on it. The y-axis is the mean absolute percentage error, so that was the evaluation metric that we used. The 4 charts represent the 4 performance variables that we're modelling, and going from left to right within each chart, you have the first 2 are the kind of naive approaches that I mentioned, and then the 3 after that are the more sophisticated approaches. And these are the distributions for the MAPE score for each of the kind of different lengths of data inputs and the lagging that we did for the predictor variables. So you can kind of draw a general picture from that the 3 more sophisticated approaches outperform the naive approaches on most of the performance metrics. The one that did best generally is the second from the right, which is the random forest model that's modelling the change in the outcome from one year to the next. And the overall kind of the worst performing best model was the proportion of A&E attendances over 4 hours, the top left one. So that was the hardest one to get a good evaluation on. On to implementation. So I did this, it's a Shiny app, which I developed using Golem. And it's deployed to Shiny Apps.io using just a free account. Free accounts have big limitations on usage, but that's the way we've done it at the moment. And if people are using it, we might have to rethink it. It's publicly available, so it uses public data, so that's fine. It's very easy to set up. As it's written with Golem, it's a package as well. It's an R package, so you can actually install it and run it locally, just like you would any other package. And then you can also run it with the Shiny run GitHub command as well, so you can run it locally from the GitHub repo. So there's lots of options there, but it is on Shiny Apps.io for people who have less kind of less technical skills. So what does the tool look like? You can just about see that. So this is an example output for one of the 4 performance metrics. This is the A&E 4-hour wait. So it's for ICB chosen at random. And in yellow are the observed values, the published data. And then the dashed lines are 2 different scenarios that the model predicts. The first scenario, which is the kind of the one that finishes horizontally, is what if all future years, the inputs to all future years are the same as the last published value, the last observed value. And so that's what the model predicts. And then the second, the kind of the one that's sloped downwards slightly, is a scenario where we've used that same kind of baseline, but then we've actually decreasing bed occupancy by 1% every year. And so that's the impact on what the model predicts for 4-hour waits over the next 5 years. So on to learning. So as I said, I was quite new to the method side, the modelling side. I've always been quite overwhelmed by what statistical packages are available in R, so I used tidy models. I'd always wanted a reason to kind of learn it a bit better. Tidy models is great. It does everything pretty much that you need, and it's in a familiar tidyverse language that you might be used to. Loads of documentation examples out there, which is great. And something I didn't realise until quite late in the project, that it safeguards against a lot of common errors you might have. You might do without thinking about it. So that's another great piece. So if people are thinking of getting into modelling, that's a very simple choice. And secondly, I also learnt Gollum for this project, and it was a great kind of framework to use. It sets up your project for you. It makes it easy to know where to go for what. It's quite tricky to debug it, though. I think that's the same with most Shiny apps, but it gives your project a bit of structure that a lot of Shiny apps don't give if they're kind of thousands of lines of code in one R script. So, and it's got all these other features with it that help you kind of make a good bit of software. So I'll stop there. Thanks. And if anyone wants to use this, please get in touch and we can have a chat about it.
Thanks very much, Seb. We've got a few questions and we've got a few minutes, so
Okay.
Should be good. Let me check. Yeah, here we go. Right. Okay. Could you tell us a bit more about how you took provider-level aggregate data, got commission data, how you went from to ICB of residents?
Okay. I don't, if in case people, I think your microphone cut out a bit, so I'll repeat the question. So I talked about how I aggregated from acute trust to an ICB or ICS resident geography, instead of just adding up the acute trust. So I took it's hard to explain, but I took a weighting approach. So the Office for Health Improvement and Disparities, they publish catchment populations for trusts based on hospital admissions. So I used that to understand kind of the number of people from MSO, middle layer super output areas that attend trusts, and I essentially used a weighting approach to go from who's going to the trusts, and then I weighted kind of according to. So I've got a trust value. I understand who's in the MSOA, so I weight that trust value into the MSOAs, and then I weight it back again into the geographical area.
Thank you. It's working now. There's another question. What drove your decision to use machine learning for this project? As you are keen to understand the drivers of performance, did you consider more statistical approaches like latent variable modelling or others?
That's a good question. I think from my simple understanding of it, I needed something that would be able to help me deal with a wide data set compared with a short data set, and that kind of the two approaches I described seemed to be the ones that were quite good at handling that situation. But I will have a look at what the question has suggested for developments.
Thank you. And then there's another question. Does the model take into account COVID and chaotic Tory governments?
I couldn't find a metric for chaotic Tory government. It does try and account for COVID. So I have got a variable in there for proportion of beds with COVID patients in. But I'm not sure it's very helpful. So it does currently have that, but I think I could do something better.
Thank you. So we're at time, but if you perhaps have a look at the Slack channel, there are one or two more questions cool. to answer on there. That'd be great. Thanks very much, Seb.
Thank you.
Thank you. I think next up is Chris, who's I can see making his way. Chris is going to talk to us about, he's going to explain or predict how different modelling objectives change how you use the same tools. Thank you.
Thanks. Hi, everyone. So my name's Chris Mainey. I am a head data scientist with BSOL ICB. I thought maybe I'd present a piece of work that I'd done this year, and then I realised I didn't have anything that I could parcel up nicely, so I'd rather just stand on a soapbox instead. So I hope that's all right with everyone. I like to start with a nice picture. So that one, I used DALL-E 3, which is an OpenAI image generation tool that you tell it what you want through ChatGPT as your interface. So I said, give me a cartoon that explains the difference between explanatory statistical models and predictive machine learning models. So biased input there already, right? So as you can see, sort of looks vaguely convincing, but then the more that you look at it, it's got some kind of weird words in there. I think if we are, over-interpreting our models, as is often the case from some of our customers, maybe we can draw the conclusion that ML practitioners wear long ties and statisticians wear bow ties. Yeah. Anyway, so yeah, thoughts on prediction error and whether or not your model truly says what it says. So this talk I'm drawing quite heavily on a paper by Professor Galit-Shmeli that I picked up ages ago, actually, when I was studying. And it was at the time kind of lamenting the confusion between whether or not, I guess, real statistics was explanatory and machine learning practitioners were just kind of playing on the edges. Because that was, in some ways, forgive me academics, that was kind of to a point, I guess that was kind of what the academic vibe was, at least in the area she was writing it in. And people who were building predictive models were kind of people, maybe in practice, who weren't doing anything too rigorous at the time. I would say, though, and actually Professor Shmeli was kind enough to express a similar view to me this week, that with the advent of the accessible machine learning frameworks and loads more online training and probably a whole generation of people who've learned through things like data camp or other things like that online, with the accessible training, we've probably swung the other way now, where I'd say most people are maybe familiar with predictive, but maybe not so much with explanatory. So I thought maybe I'd try and take a little tour through these things today. And I'll just throw a classic quote at you if I could, from George Box. So, since all models are wrong, you might have heard this one before, the scientist must be alert to what is importantly wrong. It's inappropriate to be concerned about mice when there are tigers abroad. So, our models are wrong, right? They are. That's fine. But it's important to know what's a sort of deal breaker, I guess. And that's some of the things I'm going to help point out today, I hope, with some examples in R and Python. So I'm going to ask you to keep this in your mind all the time. What is my question? Why am I doing this? What is it I'm modelling? What's my question? So Professor Shmeli splits models into two classes, really. So the first objective is to explain. Now, there's plenty of subclasses underneath these things, but broadly we're going to call these explanatory models. And we're trying to say, how do a bunch of things explain something else? That might sound very obvious, but it gets more complicated. Broadly, there's probably two groups. So one's descriptive, so we're trying to understand what's going on in a particular data set, and the other is maybe causal inference, which is maybe a more formal approach, often with designed experiments or with specific ways of doing it, where we're trying to say, does X cause Y, and how certain can we be of that estimate? Then there's prediction, where with prediction we're trying to say, given our inputs, can we predict something? We don't really care whether or not it actually causes it, but if it's correlated enough to predict it, can we use that to predict it? That's often future time points. It might be on a different data set. It might be on all sorts. So, and forgive me, don't get scared. I know not everyone likes a formula. I don't generally, but it's the easiest way to explain it. We're trying to say here, broadly in an explanatory framework at least, that we've got Y, and Y is caused by some function of X. Now, they could be concepts. So Y could be depression is caused by a whole set of situations. It could be life experiences, it could be economic hardship, it could be all sorts of things. It doesn't have to be things you can measure with data just yet. So the basis of an explanatory model is some theory. So you're trying to say concept Y is predicted by some function of concepts X. And really what you're interested in is F. But to do this with actual data, we need to change it a little bit. So we need to model with things that we've measured some sort of expectation of an estimate of Y with some function of other things we've measured, which is X. So we might need to model an expected depression score, for example, based on a bunch of factors we know about patients in a trial, which would be function of X. But then our goals are a bit different depending on what we're trying to do here. So for explanatory, we're using those estimates of F on measured stuff to estimate the high functioning concept of X, So we're trying to say, does this cause the whole concept? Sorry, I'm waffling a bit here. Predictive, we don't care. We just want to know what the next Y is going to be. And that's really the point of that model. So just as a slight aside, I've used causal inference, and that might sound like just a couple of buzzwords, but it is a whole field, and there's a couple of other people in this room who I went on an amazing causal inference course with, who probably have a similar thought ringing in their head that this is far too complicated to go down that in a talk. But with causal inference, if you're trying to say, in this particular case, can we say that, forgive me, I need my presenter notes. So we're trying to say, does chemotherapy cause venous thromboembolism in this particular case? But there's a whole bunch of other things that affect that path. So when you're building your model, you need to work out what relationships actually interact with each other, and where do they confound each other, and where do you need to adjust for them and not adjust for them, and where will you be getting the wrong opinion. So actually when people build causal inference models, they spend a huge amount of time thinking about the process and working out what variables to adjust for. So you don't put things in just because they'll give you a better prediction. You put things in because they have a plausible link, theoretically, to the outcome. So let's have a look at some code. So in order to kind of show some differences, some very surface level differences, because obviously they're a big deal to model them properly, I've picked some data from Kaggle. So this is data related to heart failure, and this particular paper was trying a bunch of different predictive machine learning methods to say whether or not they can build a good model, essentially. But they worked out that using just creatinine and ejection fraction measurements alone, they could get a very good model without all of the other predictors that are in the data set. So I'm just going to take those two predictors and we'll look at them from how you might code them for explanatory versus predictive. Going to use logistic regression, which is mentioned a few times by people today. Not everyone is a statistician or a machine learning practitioner, so I realise that might not be as obvious maybe to everyone. So I'm going to attempt to do regression in 2 minutes. Because why not? So with regression, which is a sort of a kind of foundational statistical method, we're trying to estimate y, so this vertical axis, with something else, so x, on this horizontal axis. And if you look at this kind of cloud of points, you'd probably say that, as x increases, it looks like y increases. And it sort of does, and maybe you might want to fit a best fit line through that kind of average relationship. That's what you're trying to do with a regression model. So you're trying to plot through that cloud of points the kind of average fit across the data set. And if you zoom in to the bottom corner of that, which are just the 2 points, what you're actually describing it with is firstly this alpha in the bottom corner, or the intercept, so where you've got a 0 value of x. And then for each value of x, how much does that line go up? So that's what your beta is. So you could say starting at alpha, and then x times beta gives me my predicted value. And that's what the linear model is. And the linear model is kind of foundational to lots of other methods. So if we're predicting y, we can say we can work out what y is by the starting value alpha plus x times a certain amount plus some error. But I said logistic regression, didn't I? Not linear regression. So, of course, let's make it a bit more complicated, because why not? But actually what you do is you zoom out, because not all data sets are kind of normally distributed. They're not all related to each other in a linear way. But actually you can make this much more general and say that some function or expectation of y, so that's what that g mu is at the beginning, is predicted by an intercept plus some coefficients and x. And that's actually what logistic regression is doing. It's not doing it on a linear scale, it's doing it on a log odd scale. Also called logit function is applied to the data. So it's a regression model that's transformed onto a logit scale. So how would you do that in R? So this is my kind of explanatory take. So here I'm putting the entire data set, which is that heart failure DT, through a GLM, a generalized linear model. And I'm predicting the death event using serum creatinine column, that's my first X, and my second one, ejection fraction. And then I've got a model summary underneath. So you can see that underneath, although it's a bit garbled and texty there, what you've got is the column that says estimate, that is a regression coefficient, so that's the beta that we talked about before. And the intercept, that's the alpha we talked about before. So that's what we've got going on for that model. When you piece them together, explains the relationship in that data. We can use them to predict the log odds of death. And for those Python users, a similar sort of thing. I'm using stats models here. I'll say more about that in a minute. But again, I'm using the formula interface to it here. So I've got the same formula you've just seen in the last one, fitted to the data set. And again, at the bottom there, we've got the coefficients, so the intercept and the betas. So I've fitted a model. Is it any good? So normally you might want to now diagnose this, test the fit, see whether or not you think it's done a good job. With an explanatory model, what you're interested in is the relationships and the interpretability of it. So the thing that you want to do, first of all, I'd say, is look for the significance of the model coefficients. So there are often tests applied to them, and you can use them as a measure of that. But also the assumptions of regression are quite important. So I won't go into them today because that's another path to go down. But are your assumptions being met? And is the model giving you some sort of association with the things that you've hypothesized? You might also want a measure of the variance in the model. So underneath here I've used the AUC, or the area under the receiver operator characteristic curve, which can be interpreted roughly as the proportion of the variance your model explains. So 0.76 there, 76% of the variance explained. So that's two ways of doing it, R and Python. So that's the variance, the significance of the coefficients, and the assumptions of the technique. So is overfitting an issue? Because that's one thing that a few of you who work with ML might immediately ask. Because I fitted the whole data set there. I haven't held any back. I haven't done any testing outside of it. Well, I'd say think about what we're doing here. So if it's an explanatory model, I want to explain the variation in my data set. I don't care about whether it generalizes to another situation necessarily. That's not my modeling objective. So I would say that overfitting is more of a predictive issue than is an explanatory issue. So why did I use stats models as well for the Python users in the room rather than scikit-learn? It's because scikit-learn is wonderful, but it is built for predictive models. It's built for you to throw lots and lots of things through it and treat them in loads of different ways and work out which one gives you the best predictions. And if you look in the documentation, it has that little box I've highlighted at the bottom there. And it says regularization is applied by default. Now that might sound like jargon, but what that is it did a regression for you, but it applied some penalties to it to stop it overfitting. Now what that immediately does is it biases it, and it means that you can't interpret the model coefficients. You can still use it to predict, because that's the goal of scikit-learn. But it's not in stats models. Stats models is a more classical statistical approach of it, I guess. So for those of you who are Python users, if you use scikit-learn, don't assume you can build an explanatory model for it unless you're very clear on what you're doing. You can, of course, turn the regularization off, but that requires you being aware of what it is to turn it off. Okay, so I've talked mostly about explanatory. What about predictive? So I've treated this slightly differently. So what I've done here is the two columns I had going in, which were the serum creatinine and the ejection fraction, I've chosen to scale them this time. So the scale function here divides it by the mean, takes the mean away and divides it by the standard deviation. So it scales it so that a unit of 1 means 1 standard deviation above the mean, or minus 2 standard deviations below. It's a z-score, if you know what that is. But that sort of normalizes the differences between the different predictors. They're on the same scale now. I've then split it underneath into 80 and 20%. So I'm going to use 80% of my data to train the model and 20% to hold out to test it, which is what you've seen in Seb and Scarlett and other people's approaches before. We've had holdout samples, we've been training a predictive model and then be looking on performance on an out-of-sample test. But it's the same model, it's the same GLM, it's just on a smaller data set. But importantly, when I test my AUC, what I'm doing is I'm testing it on the 20% I held out, not on the full data set. Because my objective is to predict. So my objective is to say that given my trained model, how well does it do on other data? So the objective of the prediction model is different. And similarly here, a Python way of doing it, where it uses a standard scaler, which does the same thing. Used scikit-learn this time. And I have actually turned the penalty that I said about before on that previous slide off, but by default, scikit-learn would apply a ridge penalty, for those of you who know what that is, which would shrink the coefficients. But again, AUC is slightly different here, and that's not because scikit-learn did a bad job, it's because I've taken a random sample of 80 and 20 out of the data set, so it's going to be different. So really, I should do this probably hundreds of times and average over them. But we've just done one for today. So I've talked a lot here about the importances of different approaches. With an explanatory model, what you care about is a plausible relationship. You're trying to estimate the effects of some concept on the thing that you're trying to understand the relationship with. You want interpretability. You don't want crazy esoteric transformations of your predictors. You don't want to be dividing them by all sorts of weird functions and not be able to understand them. You want to know and be able to understand what goes into the model and whether it's linked with the output. You're interested in minimizing bias. In a prediction context, I'm probably happy to accept a bit of bias if, in general, it gives me a bit less variance. And you may have heard of bias-variance trade-off, and that's where it starts to come in there. Similarly, though, with prediction, I care about my fit on new data. I don't care whether or not it's related. I don't care whether or not it's strictly causal. It's just whether or not I can use it to predict the data. But the advantage with prediction models in this sense is I can engineer the heck out of it. I can transform all the inputs into whatever way I want if it helps my fit. So in terms of advice on the scaling as well, I would say the only reason for you to scale in an explanatory model on the inputs is because you have a plausible reason to. So if you think there is a logarithmic relationship between one of the inputs and the output, then do a log transform. Don't just do it because it's a better fit. It has to be a plausible relationship. Whereas I don't care in a prediction model. If it gives me a better fit, transform away. So why am I labouring these points over the different models? Because I want you to consider your approach when you're modelling something. Are you trying to explain the differences between things, the relationships between them, how the concepts are connected in some causal fashion, or describe it? Or am I really interested in predicting future or out-of-sample data points? So to test you all, I thought we'd play bingo. So, and I'm sorry, people at home, you can't raise hands here. But can I get a show of hands for each of the following ones for predictive or explanatory? So we'll go explanatory first. Explanatory, so forecasting attendances at A&E department. Is that an explanatory or a predictive thing? Explanatory? I'll take that as a no. I'm going to just go straight for predictive. That's a really clear predictive thing, right? Next one. What drives people to attend A&E? Explanatory? Ah, lots of hands. Interesting. Predictive? Yeah, it's an explanatory one, I would say. Now, and it's okay that that's a kind of woolly question, and I haven't pinned that down to individual data items, because that's how you would start an explanatory model. What's a person's risk of attending an emergency department? Explanatory? Predictive? Quite a few unsure, but more predictive, I'd say. I'm going to sit on the fence. It depends. Is it about the individual risk, or is it about what explains it? I suppose you could do that one in either context, depending on how you want to use it. Did our new urgent treatment centre pathway decrease how often people attended the emergency department? Explain. Yeah, lots of explains. Predict. 1 or 2. I say that's explain, because again, it's about the relationship. And I would actually say that that's probably one of the major cases in a lot of health service research. When you're doing evaluation of something, you're probably trying to build an explanatory model, whether or not you quite realise it. Even if you're incorporating simulation elements, you probably have a wider explanatory model at play. Building a large language model to answer questions through a chatbot. Would that be an explanatory model? No hands. Predictive model? Yeah, lots of hands. Yeah, I'd say that's a fairly clear predict. And last but not least, modelling long-term population health state changes. So by that I mean person who was in one health state, maybe well, deteriorates into not well, for example. Predict. A few hands. Explain. Now, I'm the first to say that I'm not an expert in that, but I'd say it depends, because it depends on what you're trying to do. You know, are you interested in what causes that shift, or are you interested in understanding how that shift happens in your population so you can predict it in the future? Okie doke. So, oh, my clicker's stopped. There we go. So, in summary, I wanted you to keep asking, what's your question? And I know that's an annoying thing to keep asking yourself, but when you're setting out to model things, it's not always clear the objective of what you've been asked for. We had a fantastic example earlier on about give me all the data on the dashboard for everything now. That's often how questions come at you, right? So you have to think about your modelling context and what is it they are trying to answer before you start about trying to model it. I'd say, is it predictive or explanatory? Is the objective of this talk? So if you're following a particular framework, say explanatory, don't get caught in things that maybe don't fit with that framework. Don't get caught in overfitting, for example. Or maybe if you're trying to build an explanatory model, you're probably best not going down regularized models. You're probably best not touching XG boosts and lasso regressions and those sorts of things. You need things you can interpret. So today we used logistic regression. We looked at how you could use that in a very basic capacity in either front, and if you were doing it in the real world, there'd be a lot more thought behind it than the things I've shown you. But all of this is available online, so I'll drop into Slack after this the links for it if it's of use to anyone. Thank you very much. I don't expect you to read that. It'll be there if you want them.
Okay, thanks, Chris. There's a lot of questions, so it's going
to
keep you busy afterwards, because we've only got time for
I'll jump on Slack. Yeah.
I'm going to pick the couple with the attracting the most emojis, because that's all we're going to have time for. So the first one, do you think we suffer a bit from lack of theory in health or healthcare analytics, so we struggle to have a common language about what we're trying to do in analysis and modelling? Maybe contrasting that with fields like economics and epidemiology.
Yes, I would say, in my opinion, but that is not always a bad thing. So sometimes we are very pragmatic in that we need to get an answer for something tomorrow because it needs to go in the board paper, and you've got to do what you've got to do in order to inform your organisation for that time. If we were doing it well, we'd have a lot of time up front and a good timescale to think about the problem and to describe it and to build it properly. I think education is a key thing here, and it was great to have a master's presentation just before. I had a couple of them actually. The thing that taught me the most about statistics was realising I didn't know anything about it, and I suddenly had to know something about it. So I went and studied. And study is not something that everyone can always do. They can't always afford to, they can't always be supported, etc. But if we were somehow able to offer that education as widely as possible and establish some standards in how we approach things, I think that would uniformly help. But it's probably naive to assume that would happen, right? So I think maybe we do suffer from a lack of rigour in terms of our approach to modelling things, but it doesn't mean we should stop trying.
Thank you. And the final one is just to ask if you are starting a flame war by showing code with leading commas.
Yes. You might have noticed a few typos here or there. I might have flown my slides in at the very last minute.
Okay, right. Well, there's plenty more questions for you to answer on the Slack channel.
Okay,
so
will do. Thank you.
Chris.
Thanks.
Okay, and next up is Ruth Keane, who is going to present to us. There's a slightly different title. Which one shall I go for? This one or that one? I'll have this one. I'm an open source girl in an Excel world. The benefits of Open XLSX2. So over to Ruth.
Hiya. Hi. So, I realised I didn't put my name or job title on there. So I'm Ruth Keane, and I'm a Principal Insight Analyst at Arden and Gem. I do appreciate it's a bit contentious coming to the NHSR conference and talking about Excel, but I guess, I'm not necessarily trying to convince anyone that you should be using Excel. It's more about how can we use Excel in kind of nice RAP pipelines. So that's kind of the context of this. I'm hoping. There we go. So I'm going to start with just talking a little bit about reproducible analytical pipelines in Excel, and then I'm going to talk about creating some simple Excel files in R, and then talk about creating more complex Excel files. But firstly, reproducible analytical pipelines. This is not the first time we've spoken about these today, and it will not be the last. But this is basically automating your analytical processes, minimizing the manual steps, using open source software, using version control, making it very auditable and well documented, and adding testing. The advantages of these is that you often end up with analysis that's less prone to error, more efficient, quicker to run, and improved quality of analysis and trust in the analysis from kind of using auditable processes and code. Back to Excel. So Excel is very accessible and quick for people who don't know how to code. People like getting their data in Excel because they can do, a few odd calculations with it. They can filter. It's really easy for them to do things. It's also quite aesthetically pleasing. You can have nice graphs in there. You can even have pivot tables, and complex analysis in Excel is possible. And this is kind of where we end up with in a lot of kind of public services, is really complex analysis happening in Excel because it's technically possible. So why not Excel? So it can be quite error prone. I think, it's quite easy to have errors with dates or with copy pasting things wrong. It can introduce quite a lot of error. It's also particularly time consuming, especially for trying to do more complex analysis. And again, it's quite inefficient for that. But the main issue really with Excel is it's not built for automation. And so it's not necessarily very good for that sort of thing. And I just had a quick look on a couple of government sites looking for Excel outputs, and it didn't take me very long to find a few. So here, one from NHS England and one from ONS. The kind of conclusion of this is many stakeholders still want Excel outputs, even if they're open to and happy to use a reproducible and analytical pipeline. So there are a few different options for creating Excel. I've put a little thing at the bottom that this is possible in Python. I mostly use R, so I'm going to talk about R here, but I am aware of the XLSX writer package. But in R, we have a few different options. There's Write Excel, which is kind of the tidyverse style of package. It's very easy and quick and simple, but it can't really do formatting. And a lot of people are very keen when they're kind of automating Excel processes to retain nice formatting. There's also XLSX and Excel Connect. These both require Java, so can be quite difficult to set up. So I haven't really gone into them because it's just logistically quite difficult. And so the packages that I have looked into are OpenXLSX and OpenXLSX2. I managed to pick a topic for this presentation that I can't consistently pronounce, so apologies if I trip over myself with OpenXLSX2. But yeah, the kind of main difference in these packages is that OpenXLSX2 has more advanced formatting. There's a couple of things you can't do in OpenXLSX, and it's got slightly nicer syntax, I think. So the features that it has are you can have multiple tabs with different things going on. You can have complex styling, so borders, fonts, backgrounds, change the width of rows, and you can do all sorts of things and add conditional formatting as well. You can also put in images and pivot tables. You can have plots, and you can put formulae in, so you can have things that kind of will continue to, if you were to change the numbers, will continue to recalculate. But at this point, I think about the quote from Jurassic Park, where your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should. And I think there is definitely a danger with OpenXLS X2. It's because you can do all these things, you probably should think about whether it's the right choice. So I've just had a little think about when you might want to consider using a package like OpenXLS X2. So if you're wanting a wrap process where you need the output to be Excel, so if the stakeholders or users are very keen on the Excel output, if the output is quite complex, like visually, if it has some kind of styling elements, it's worth thinking about, and if the analysis is going to be done more than once. So it might not be worth it if you're making kind of a visually complex spreadsheet for a one-off analysis. In that case, it probably won't be worth the development time. Additionally, if you don't need the formatting, you could just use a CSV file. So it's not worth kind of making it pretty formatting for the sake of it. And again, if you're wanting to come up with, a lot of people like Excel dashboards, or I guess they're called Excel dashboards. They're not really a dashboard, but when people want that, I think that's probably when you might want to push for an alternative dashboard and think about a different output. So this is kind of my brief guide to using OpenXLS X2 for anyone who might need that on a project. So I think it's got quite a nice syntax. So the way you use it is you build up a workbook. So you create a workbook with WB workbook, and then you add a worksheet, and then you can add all sorts of things to your worksheet. So here I'm just adding the iris inbuilt data from R, and I'm adding it onto the tab I've called tab name, and then I'm saving the output. So this will just add the data. So if I'm wanting to add some styling to that, I then add I call WB add font to add font, and I can change the color and the size and the style. I can also add like a background, so add fill and add border, and all of these I tell it what tab I want this to happen on, and I also give it the dimensions I want this to apply to. So in this case, my dimensions heading object will just put this styling on the top row, and you can also set column widths as well. And then once I'm happy with this, I can then save this workbook, and then all of this will appear in my output. So this is this example. So the code I've just shown you will make that, and it's obviously quite a simple output. It makes basically the data's there, and the top row has got some interesting styling. And just briefly, I wanted to talk about the two different ways that you can use this package. So we've got piping syntax, and so this doesn't modify in place. So you can see I overwrite the WB object when I add all the things to it. But you might also see the chaining syntax, and so these do modify in place. So this is just worth knowing about, because you might see both of these online, and it took a while for me to get my head around why that was happening. If we think about the output I just showed you, we basically have got one element of formatting. So we've basically just got some formatting on the column headers. But say if we wanted the main body to look slightly more interesting, we would need formatting for two separate sections. And even with this, I don't think it's complicated enough, because what if we wanted to add some conditional formatting to some of the columns? And what if we wanted to, say if we had locations and we wanted to highlight the different locations in bold, for example, we'd need separate formatting for 4 sections. And then if we then wanted to add some title information, add some more interesting conditional formatting, we'd need separate formatting for 8 sections. And then if we want multiple tabs, then we're going to have to repeat this multiple times. And so this is where I've kind of worked to kind of create some functions to create more complex reports. So this is the type of report that I've been working on. So you've got a title section at the top, a kind of row info section with this, in this case it's the empty cars data set, so it's just the brand names, and then the main body. And the way this works is we can have multiple sheets that follow this same pattern, so title section, row info, and main body. And the title section and row info will stay pretty consistent, but the main body can change. So we use a for loop to create each sheet. So we iterate through an object with the data and parameters that we need and call the write sheet function. And then the write sheet function, which I've created, will create a new sheet, and then it will add the title section, add the row info section, and add the main body section. And the first two, the title section and row info section, is quite simple. It adds the data and adds some styling. But the main body section is where you can put the complexity in. So within it, you have a style name argument, and there's some conditional logic which will call different styling functions depending on what style we ask it to use. And so this means we can create a more complex spreadsheet without having to change the code too much. So we can create, with this code, we can create this, but then if we change the style name to months with total, then we can create this, which displays quite different data and quite a different visual, but uses mostly the same code. And again, if we wanted to add a new style type, most of the code would stay completely the same. We just had to make a new add main style function. So my conclusions on OpenXLSX2 is that if you really need Excel, it can help you out. You can create simple or complex Excel files pretty easily, but when you're doing more complex things, you should definitely look at functions and planning out the document quite carefully. And then briefly, because we like open source things, I just put some information about open source alternatives. So Read ODS is a package that does allow you to write ODS files, but you can't have formatting. So you'll have to convert. You'd have to convert from the Excel file either manually or within R. And then finally, this work was based on a project I did with NHS England, so the elective analysis and RAP teams. And so with thanks to Debbie, Chelsea, Nicola, Laura, Warren, and Jen, who spoke today. And the code is available on the AGEM GitHub. And any questions, you can get in touch on Slack.
That's great. Thank you very much, Ruth. So just before the break, then there's time for a couple of questions. There are plenty here. I'm just going to try and... Some of them have come on and then you've kind of answered them as the talk's gone on, so I'm just trying to pick out something that would be helpful. Okay, so how does it handle problematic data like dropping leading zeros?
So the way it works is you will give it a data argument, and so when you have the WB add data function, you will just tell it what data you want to add. But there are certain, you can control certain elements, so you can have it respond to certain. So you can say if there's a missing value, I want it to be an NA, or I want it to be an empty space. So and that might be control there, but this is more creating the output. So really, in terms of like leading zeros, you probably are going to want your data to already look mostly right before you put it in your spreadsheet.
Okay, thank you. And then another question is a very unique talk. What was the inspiration? And what message do you want to send?
I guess I worked on a couple of projects this year where despite kind of people's enthusiasm about RAP, they still wanted to retain Excel, and so I did have to kind of pick up these skills, and I didn't really, and I found a few resources online, but I felt like I was missing the like kind of basic intro on like how you might use this to automate something, and so I thought that might be useful if anyone else is in the same situation.
Great, thank you very much. So there are still quite a lot of other questions in the Slack channel if you want to take a look there later. Also, not just questions, but for other people in the audience who are interested in this topic, there are also quite a few useful comments and suggestions from people about other packages that are kind of related to this, and advice on government advice on releasing stats in spreadsheets, for example, or other packages like Office R for automating Word and PowerPoint files. So people might like to take a look at the Slack channel questions on this particular talk, because there's quite a lot of useful information in there. Right, I think that's it for this session. Thank you very much again, Ruth. And we're now on the break, and we are 30 minutes we have, so back in here to resume at 3:35.